Welcome back to part 2 of this lecture series on multidimensional diffusion. This part, we'll talk about how multidimensional diffusion encoding, which originated in NMR, is being adapted for use on imaging systems. Multidimensional diffusion coding was first proposed in the context of NMR by Mitra in 1995. In this first implementation, a double spin echo was used with two sets of gradient pairs, and Mitra demonstrated that the signal dependence on the angle between the two gradients could be used to distinguish effects of restricted diffusion from those arising from a distribution of different diffusion constants. Following this in 1999, Cheng and Corey showed that they could quantify eccentricities and symmetries of confining cavities, even when there was no bulk order in the sample. And they demonstrated measurements in yeast cells that had different eccentricities. Nearly a decade later, Ozarslan and Basser presented a theoretical paper, still in the context of NMR, that calculated the exact expression for the NMR signal attenuation from restricted geometries, including parallel plates, cylindrical pores, and spherical pores. And this work built largely on formulas presented by Callahan. Additional NMR experiments were presented around the same time, demonstrating the angular dependence of double diffusion encoding in polymer beads, radish, and porcine spinal cord, as well as microcapillary tubes and also in fixed neuronal tissue samples. But it wasn't until 2011, Noam Shemesh won the ISMRM Young Investigator Award for his paper demonstrating multidimensional diffusion MRI in the in vivo and ex vivo rat brain, which I believe was the first imaging demonstration of the technique. A couple of studies on human MRI scanners followed not long after. Avram et al. Performed measurements along the corpus callosum, and Lorenz et al. Demonstrated initial images in the in vivo human brain. So there's a number of challenges associated with implementing double diffusion encoding on clinical scanners. The additional encoding pair creates a longer encoding period in the sequence. The need to sample many different orientations as well as multiple angles between the diffusion encoding pairs creates a long total acquisition time. And lastly, the more limited gradient strengths of human scanners compared to small bore scanners, although we've seen some advances, they are still somewhat limiting for this type of encoding and require longer diffusion encoding gradients in order to achieve sufficient diffusion weighting. And that just results in additional signal decay. So in this part, we'll look at ways that each of these challenges is being tackled. And to start, we'll look at how to reduce the sampling schemes required. So this was something that a graduate student in my lab looked at. How can we reduce the number of acquisitions without compromising the measurement of microscopic fractional anisotropy? And at this point, the proposed acquisitions normally included some set of parallel and anti-parallel gradient pairs that were uniformly distributed on a sphere, a set of orthogonal gradient pairs, normal with the normal vectors to the plane that those orthogonal gradient pairs defined, distributed on a sphere, and then also some uniform rotations within each plane. And the key realization here was that clinical scanners operate in the low Q long diffusion time regime, again, because of those limited gradient strengths. And that means that individual subvoxel tissue components can be modeled using a Gaussian propagator. Orthogonal encoding takes the trace of the in-plane diffusion tensor for each subvoxel compartment. And since that trace is rotation invariant, the in-plane rotations probably weren't adding a lot of information in this case. So to look at this, we did some simulations of in-plane rotations for an infinite cylinder. The figure on the left shows results for the cylinder oriented along the x-axis with diffusion encoding in the xy plane. And the plot shows the signal modulation as a function of the angle between the two gradient pairs. Each thin line represents a different in-plane rotation of the gradient pair, while the signal modulation varies for different in-plane rotations. The signals all intersect at pi/2, indicating that the signal is independent of the in-plane rotation, when those two gradient pairs are orthogonal. And so the plot on the right shows that the signal variation for in-plane rotations is also negligible for a range of different cylinder radii corresponding to the expected range of axons in the brain. We also wanted to look at the effect of different numbers of encoding planes, and increasing the number of encoding planes reduces the signal variation across different cylinder orientations. But there's a really large improvement in rotational invariance from 4 to 6 encoding planes and much less thereafter. Looking at actual in vivo images, we saw significant changes in image contrast when you look at the different orthogonal encoding planes going left to right, and much more similar images, similar contrast as you went down each column here, looking at different in-plane rotations. And so this also inspired confidence that the in-plane rotations weren't adding a lot of information. So the conclusion was that the goal then should be to prioritize the number of encoding planes, include at least 6 orthogonal encoding planes. More encoding planes can be used to improve the robustness to motion and or build up the SNR. And using these concepts, we created a 5-minute scan so that it could be tacked on to scans in the clinic and start to be deployed for testing in clinical situations. And this is an example of the image quality for the microscopic fractional anisotropy maps on the bottom row for that 5-minute acquisition. Okay, so let's look at this long echo time that's required to accommodate the additional pair of encoding gradients. Probably the biggest development that's helped push forward multidimensional diffusion encoding has been this realization that we don't have to use these rectangular pulses and play them out separately to acquire this type of diffusion contrast. We can use much more generalized diffusion encoding waveforms that provide a framework for maximizing the use of all available encoding time in the sequence and optimizing for scanner-specific hardware constraints, such as gradient heating or duty cycle. If we look at the triple encoding or the isotropic diffusion encoding, this encodes a trace of the diffusion tensor, which is rotation invariant. And so it also allows us to use the full gradient amplitudes on each axis simultaneously, which is very efficient. And the numerically optimized waveforms can also reduce the encoding time compared to playing out the separate double or triple diffusion encoding with pulse gradients. And so we can reduce our echo time that way. Microscopic fractional anisotropy can then be measured using a combination of isotropic and linear diffusion encodings. I want to stop and take a moment to point out that there is a variety of different terms used for this type of encoding, and want to say that they are all within the same family, and to be aware of this when you're looking in the literature and trying to look up what's been done in this field. So generalized diffusion encoding waveforms, tensor valued diffusion encoding, multidimensional diffusion encoding, double triple diffusion encoding, planar spherical diffusion encoding, Q-space trajectory imaging, magic angel spinning of the Q vector, double triple multiple pulsed field gradient imaging. They are all used, and we haven't sort of narrowed in on a consensus here, but lots of good work being done. Okay, to further go on and look at this robust, efficient isotropic diffusion encoding waveform design, the numerical optimization produces generalized diffusion encoding waveforms that maximize the use of available diffusion encoding time and gradient system performance. Many equally efficient waveforms can generate the same diffusion contrast. And we can really use that flexibility to improve robustness to gradient imperfections like eddy currents and concomitant fields. And so that's where we thought we'd try to do some optimizations for this type of encoding. So Grant Yang, again from my group, he modeled the effect of eddy currents as a simple convolution of exponential decays with a certain given time constants with the gradient slew, and just enforced the requirement that these eddy currents were 0 at the time of the image readout. And there was already this beautiful optimization framework available that had been developed by Joland, and it provided a very easy way to add an additional constraint and develop or design gradient encoding waveforms that had this inherent ability to null the eddy currents at the time of the readout. And so you can see on the left example, the waveforms without the nulling and the ones on the right with the nulling. And we were able to simultaneously null on multiple axes or choose which axes you wanted to null on, and overall decrease the eddy current induced field. And this just shows an example of the improvement that we were able to achieve with that. And this type of isotropic encoding with the optimized waveforms was starting to produce some really, really beautiful in vivo images for the microscopic fractional anisotropy. And we can see a nice comparison here of different slices, same brain for conventional fractional anisotropy and the microscopic fractional anisotropy. And what we see is just much more consistent signals across the white matter. And these arrows are really highlighting areas where we see a drop in FA because they're areas where we know there's much less coherence in the tissue, or there's a classic crossing fiber region, and we don't see that drop in the microscopic fractional anisotropy maps. Okay, so the last challenge here, we have made advancements in improvements in gradient strength, but we always want more. And so I just wanted to share with you an opportunity that we had to try out some of this on a unique high performance gradient system developed by Tom Fu and Exun Tan at GE Research. This is a head-only system that achieves 200 millitesla per meter maximum gradient strength, and also very high slew rates simultaneously, 500 Tesla per meter per second, which means that it also dramatically shortens your EPI readout, also reducing your echo time and reducing distortions and all those good things. And so we were eager to see how far we could push some of the resolution on these multi-dimensional diffusion encodings. And so here is an example of the microscopic fractional anisotropy maps acquired on these specialized MAGNUS gradients. There are a few artifacts here that were not resolved, but what we were excited to see was that there did appear to be some unique contrast at the edge of the cortex, and particularly at the boundary between the cortex and the white matter. And so I just think it's really exciting as we're able to push this to higher spatial resolution to see what additional details that it will provide. So in summary, multidimensional diffusion coding was first proposed in the context of NMR. Adapting multidimensional diffusion coding for use on clinical scanners is challenging due to the long encoding times, large number of samples required, and limited gradient strength. Assumptions of time-independent Gaussian diffusion are reasonable for acquisition regimes capable by clinical MRI scanners, and eliminate the need to acquire in-plane rotations, which thereby shorten scan time. Generalized diffusion encoding waveforms reduce encoding time for double or triple diffusion encoding and enable incorporation of additional sequence optimizations, and high performance gradient systems enable higher B values and spatial resolution. And that concludes part 2.